Thanks to the chair and to everyone who joined my talk. I'm Yuping Lin from Colorado Boulder. Today, I'm going to tell you about the story of the charge density waves on the hexagonal lattices. I will focus on the correlated phases at the Van Hove singularity, and I will tell you about the relevance in the kagome superconductors. This talk is based on 4 of my works done with my advisor Rahul at Boulder. For the hexagonal lattices, I'm referring to the triangular, honeycomb, and kagome lattices. On the finitely dispersive band in these systems, there will be a particular point where the dispersion energy shows a zero point. And this kind of zero point can lead to the log divergence in the density of states, which is known as the Van Hove singularity. The Fermi surface at the Van Hove singularity is universal on the hexagonal lattices. It is a hexagon inscribed in the hexagonal Brillouin zone, and the corners are at the centers of the Brillouin zone edges, where the Van Hove singularity occurs. The opposite Fermi surfaces are parallel to each other, so there will be the Fermi surface nesting at free nesting momenta. Now, combining the Van Hove singularity and the Fermi surface nesting, we could have the maximally log squared divergence at the Fermi level. So the question is, first, can the Fermi level occur at the Van Hove singularity in the practical materials? Second, what kind of correlated phases are there in these materials? In 2019, there is a new hope in the kagome metals at V3sp5. These materials are quasi-2D, where different types of atoms form different 2D layers. Particularly for the vanadium atoms, they form the kagome nets, and the kagome nets will contribute to the hexagonal Fermi surfaces at the Fermi level, as you can see either from RPAS and the DFT. So this is exactly what we want at the Van Hove singularity. Now the question is, what are the correlated phases in these materials? People have found that there could be the charge density waves at the free nesting momenta, and particularly there is a twofold symmetry breaking. That is one of the magnitudes. The magnitude at one nesting momenta is much weaker than the other two, and you can see it in the real space pattern. More importantly, there is a time reversal symmetry breaking in this CDW, and this is available conventionally from the CDW. So the question is, what is the source of the T breaking? A possible answer is from the imaginary CW. So in 2019, we found under RG that the imaginary CW could actually be dominant universally at the Van Hove singularity, as long as we have a larger fermion flavor than 4. The imaginary CWs are actually the loop currents in real space, or you can think of them as the staggered flux orders. We went back to the spin 1/2 case where there are only 2 fermion flavors, and we found that although people knew that the real spin density wave is very important and is subleading to a D-wave superconductor, they have always missed the imaginary CWs. And we found that the imaginary CWs will actually be degenerate with the real SDW. So it is also very important for the spin 1/2 case. Now, could it be the answer to the kagome metals? To understand this, we consider the interplay of the real and imaginary CWs. To do so, we consider the complex order parameters at the free nesting momenta. So you can see there is a magnitude and a complex phase. We did a Ginzburg lambda analysis to find out the ground states. We found that the ground states are actually the free Q orders, where the magnitudes are the same as the free nesting momenta. Furthermore, there is a total phase condition, where the summation of the free phases will be an integer multiple of pi. We map out the phase diagram, and we found that it is actually quite interesting. If we start from the corners where the phases are either 0 or pi, it will be a trivial insulator, which is a continuous deformation from the real charge density wave. And there will be either side or bound density modulation. Meanwhile, if we go across a phase boundary into another phase, it will be a continuous deformation from the imaginary CEWs. and it will be a Chern insulator under time reversal symmetry breaking. So the T time reversal symmetry is actually broken universally in a complex order, but at particular points, there could be an effective T under the one-side translation. And this kind of symmetry can protect the direct semi-metal, where a pair of direct points occur at the Fermi surface. And if we go away along the phase boundary, the broken effective T will lead to a single direct point semi-metal. Now, how is the phase diagram manifest in the kagome metals? In these materials, the relevant bands are actually the particle bands. And the real CDWs will manifest the inverse style of David pattern, where you can see the strong hexagon and triangles. Meanwhile, the imaginary CDWs will again manifest the loop current, and it will again be a Chern insulator. So how do they combine in the kagome metals? Let's recall that the kagome metals have the charge-density waves, where the real order magnitudes are different at the free-nesting momenta. So we can think of them as having unequal phases at the free-nesting momenta in the complex order. Now we consider the magnitudes at the free-nesting momenta and map out the real space pattern. We found that the pattern is now has a star of David pattern, where the strong bonds from the stars in the real space. More importantly, it occurs in the Chern insulator phase, so it naturally explains the anomalous Hove effect. So our theory may be indeed relevant in the kagome metals. Next, let us look at the purely real charge bond orders, where there could also be interesting things. So we consider the real charge bond orders at the free-nesting momenta on a finite hexagon. So it will manifest the 1 plus or minus delta hoppings on the bonds. At the particular point of delta equaling 1, there could be a complete separation between the hexagons and the triangles. That is, the weak bond all vanish. So this system obeys the C6 symmetry, and the question is, could it really be trivial? To answer this question, we did the computation of the energy spectra of this finite hexagon. We found that in addition to the bulk bands, there could be also be a low energy branch near the Fermi surface. More importantly, there are the corner states in these low energy branches, where the density of the wave function are localized at the corners of the finite hexagon. So how do we understand this? We can think of it as a result of an obstructed atomic insulator, where the Wannier centers are shifted to the corners of the unit cells from the unit cell center. So if we have the C6 symmetry, the shifted Wannier center will lead to the imbalance between the electrons and the positively charged ion numbers. And this will contribute to the corner filling anomaly, where the fractional charges occur at the corners. And this corresponds to the corner states in the energy spectrum. So I mean, even with the purely real order, we can also have very interesting higher order topological insulator. Finally, let me tell you about the superconductor in the kagome metals. It has been found experimentally that under pressure and doping, the CW will be suppressed across the transition and finally vanish at a critical pressure. Correspondingly, there could be a double dome superconductor where the peaks of the TC occur at the CW transition and the critical pressure. Because the TC is much lower than the CW critical temperature, we can think of them as the children of the parent CWs, and this motivates us to develop our theory. This is the phase diagram in our analysis. We consider the reconstructed Fermi surface, which goes across the Van Hove singularity at the CW transition, and this will lead to the peak in the first dome of the superconductor. So the second dome will occur at the critical pressure, where there is another Van Hove singularity. So we can consider different types of parent mechanism, where there could be the phono-mediated attraction, which will lead to the S wave, and also the deformed S plus D wave under two-fold symmetry. Meanwhile, we could also think of the superconductor as coming from the parent CW fluctuation, and this will manifest the reconstructed Pomeranian fluctuation, which could lead to the purely D wave superconductor or the S plus D wave superconductor. Finally, let me end my talk with a brief summary of the content. And thank you very much for your listening.